Hello everyone and welcome back. My name is Mr. Cobalt and in this video I'm going to be going over corrosion, those undesirable redox reactions. So let's go into this. So first, what is corrosion? Corrosion is the gradual or nearly always undesired oxidations of metals that are exposed to oxidizing agents in the environment. So basically, these are the oxidations of, like, say, metals, like your iron on your car, or the your silverware, the silver on your silverware, or the patina on bronze statues, or things like that. These would be the undesirable oxidations of metals. So let's talk about the oxidation of water, the reduction of water, because that is part of what corrosion the process of corrosion involves. So here I have the reduction of oxygen in the presence of water. So here I have oxygen gas plus water plus 4 electrons gives you hydroxide ions. And so that has an electrode potential, a standard electrode potential of positive 0.40 volts. And you can see that the reduction of oxygen is even stronger in the presence of acid. So here we have oxygen gas plus 4H plus ions plus 4 electrons gives you 2 water molecules. So you can see that the electrode potential of both of these is fairly positive. And so that's going to have a strong tendency to occur in nature or spontaneously. So the reduction of oxygen again has a strong tendency to occur, and therefore, if the reduction of oxygen occurs, then along with it, whatever's present, other substances can be oxidized. So this is what we're referring to as the oxidizing agents or the oxidation of metals. So oxygen, of course, is one of the strongest oxidizing agents, and so it wants to be reduced fairly badly, and so it's going to oxidize other substances in order to be reduced. And so you can see that from the fairly positive electrode potentials for oxygen. So the half reactions for the reduction of most metal ions are found below the half reactions of the reduction of oxygen. So if we go back to our list here, so remember this list of half reactions, reduction half reactions. If we find the reduction of water, so where is that here? So we have right there is +4. So if you go here, this would be the reduction of oxygen in the presence of water. So we have oxygen, water, and that has a plus 0.40. And then if you go up to 1.23, there we have the oxidation of the oxygen in the presence of hydrogen. So you could see that's way up there, and you could see that this is 0.4. Now look at a lot of the metals are below this. So let me get this straight here. So you could see that here we have copper. So copper is below. So we have the reduction of copper is below that. We have tin. We have, what else? We have lead, tin again, nickel, cobalt, cadmium, chromium, iron, and zinc. And so we have a lot of metals here. The redox half reactions of the metals are below that of the reduction of oxygen. And what that tells us, if you remember from the list, any redox half reaction that falls below the one you're looking at, then the one that's higher on the list has a stronger tendency of undergoing the reduction, and therefore the half reaction below that one is more likely to undergo oxidation. So in this case, if you have the oxidation of oxygen with one of the metals below it, the reduction of oxygen will occur, and the oxidation of the metal will occur if you pair them together. So that would cause the corrosion of the metal. And so you could see that this corrosion is actually the opposite process by which metals are extracted from their ores. And what do I mean by that? So when you find a metal in an ore, it's usually in some sort of ionic compound, right? So maybe it's an oxide of some sort. And so you're trying to reduce the metal ion into the pure metal itself, right? So, but in the case of corrosion, you're not reducing the metal out of, say, the ore. You're actually oxidizing the metal back into an ionic substance, or in what it would be like in the ore. So that is the kind of opposite. So corrosion would be the opposite of extraction. So here, extraction, metals are reduced in the extraction process, but in corrosion here, metals are actually oxidized. And so many of the metals are going to form oxides. So this gets to the question of, why do we use metals in the first place if they're going to undergo corrosion so easily? Well, one of the answers to that is that many metals form oxides that will coat the outer surface and then prevent further corrosion. So they form a little coating around the metal, so that way the further metal that's down below that, or below that coating, is now protected. So an example of that is aluminum. So aluminum will react and get oxidized to form aluminum oxide here, so Al2O3. Al2O3, aluminum oxide, in its pure form is sapphire. It's got a very strong structure, and so when it forms, it protects the underlying aluminum metal from further corrosion. And you can see that the aluminum here, aluminum has an standard electrode potential of negative 1.66 volts, and so that's going to undergo that oxidation. And so here, what about oxides of iron? Well, oxides of iron are not structurally stable, as we know from experience. So here we have an oxide of aluminum as an example. It forms a coating that's really strong, really stable, and therefore makes a protective coating around the aluminum to protect further corrosion. But iron oxides are not structurally stable. They like to flake off. They're flaking off. If you live in the Midwest, or on the East Coast, or anywhere where there's strong winters where you have a lot of snow and ice, they put a lot of salt on the roads, and so that causes the corrosion of your cars. And so if you see old cars like Nader on cars, that Pixar movie, he's pretty much rusted out. And what happens to rust? Well, it flakes off really easily. You could take it and bend it and break off pieces really easily. Well, what happens then, when the rust flakes off, it reveals or exposes the iron underneath, and therefore now that iron underneath can be corroded by more weathering and the reduction of oxygen. And so that's part of the reason why iron rusts or is not really good. So here's the reaction of iron. So we have iron solid is going to undergo an oxidation to create iron 2 ions and then release 2 electrons. And here you can see that the standard electrode potential is negative 0.45 volts. So you can see that that's fairly negative, so it's going to easily undergo oxidation. And if we compare that with oxygen here, this is pretty positive. So oxygen and iron will spontaneously do a redox reaction where the iron will get oxidized. So this tends to occur at defects in the iron, and that is at the surface, and these are called your anodic regions. Anodic or anodic regions because that's where the oxidation is occurring. We know that oxidation occurs at the anode or that of an electrolytic cell or of a battery. And so we call those anodic regions where the oxidation of the metal takes place. And then once the iron loses the electrons that are produced at the anodic regions then travel through the metal to what are called cathodic regions. And of course, they're called cathodic regions because that's where reduction is going to be occurring at the metal. And that's where you have your oxygen and your water moisture collecting at the metal. And so what I'm going to do next is I'm going to show you the equations and the steps by which rusting occurs for iron. So I'll be right back. Okay, so let's talk about the equations for the rusting or the formation of rust. And so here we have three reactions. So the first reaction here is where iron solid is going to undergo oxidation to form two iron ions and give off 4 electrons. And so you can see here that it has a positive uh, standard electrode potential, and this is going to occur at the anodic region, right? So we're going to be fairly positive, so undergo oxidation fairly easily. Now, these 4 electrons are then going to be used. These electrons are going to travel to the cathodic region, and the anodic region and the cathodic region are very close together. They're going to travel to that region. They're going to react with oxygen, and we have the H plus here. We have the hydronium ion here, H plus ion. And so this H plus comes from carbonic acid, which naturally forms when carbon dioxide dissolves in the water. So you're going to have H plus ions in solution from the carbon dioxide. So this is from like carbonic acid. And so you're going to have this react with the oxygen with the 4 electrons, and you're going to form water. And you can see that's fairly positive as well. And so again, this is happening at the cathodic region. And then what you have happening is you have the iron ions can then travel as well to the cathodic region. And so you got the iron 2 plus ions reacting with oxygen and water together. That's going to further oxidize the iron from iron 2 plus to iron 3 plus. And that's where you're going to get a hydrated form of iron 3 oxide. So you got the Fe2O3 with a certain number of waters. How many waters you have and is going to really depend on the circumstances of the rusting. But this is pretty much your rust. So rust is basically a hydrated form of your iron 3 oxide. Okay, and so this is what's forming when rust forms. And it undergoes this process here. Now, a few things to point out. So one, moisture must be present for rusting to occur because water is a reactant. So we see water as a reactant here to form rust. So you need to have a moist surface. Also, you need water for the ions to be able to flow from one place to another. So you need ions to be able to flow from the anodic region to the cathodic region. And so water is really important for that as well. So moisture is important for rusting. Additional electrolytes promote rusting as well. That's excuse me. That's because electrolytes such as sodium chloride on the surface of the iron is going to promote iron rusting because it enhances the current flow, right? So you need a flow of electrolytes, you need flow of electrons, and so electrolytes will then enhance that current flow as well. And so this is one of the reasons why you'll find that rusting occurs more easily in places where there's winters where they use salts on the road, right? So on the East Coast or the Midwest where you have lots of ice and snow, they'll throw salt on the roads. That salt will mix with the water and that'll get on the underside of your car, and you'll find that a lot of rusting occurs. It also occurs on the coastal regions where you got a lot of salt, sea salt, or salty air that's going to also enhance the uh, reduction of oxygen and the formation of these rust. And then finally, you have the presence of acids also promote rusting, as we saw here. So you need H plus to reduce the oxygen into water. So that's going to be important as well. And so the H plus ions are involved in the reduction of oxygen. And so lower pH is going to enhance those cathodic regions by lower pH, remember, means that you have a higher concentration of H plus ions. And so that's going to enhance the cathodic region where that is taking place. Okay, so the next thing I want to talk about is the prevention of rusting, the prevention of oxidation of metals. So how do we go about doing that? Well, that'll be next. Okay, so the next thing we need to talk about is how to prevent the corrosion of iron. How do you prevent rusting? Well, here's a few examples or a few suggestions. One, obviously, keep the iron dry. So you need water in order for the reaction to occur. So if you keep the iron dry, it will not rust. So easier said than done. If you can't keep it dry, then another way you could do it is just coat the iron with something that's impervious to water. So here's a few examples. You can paint the surface. You can put sealant on the surface. That way water can't get in. And so therefore you're kind of keeping it dry. And also you can coat the metal with a metal that oxidizes more easily than the iron. So for example, we have galvanized nails. Galvanized nails have a thin coating or a thin layer of zinc. Zinc has a more negative electrode potential, so therefore it's going to oxidize more easily. And so therefore when it oxidizes, it's going to form an oxide that is not as crumbly as rust. And so therefore it will make a protective coating around the metal. And so that'll protect the iron as well. In a similar way, finally, third, you can place what is called a sacrificial electrode in electrical contact with the iron. So basically, just like with the galvanized nails, you want to have a metal that is going to be more easily oxidizable compared to the iron. So if you put that into contact with the metal iron, then that metal will be oxidized first before the iron is. And so that way it's protecting the iron from rusting. And so you'll see this a lot of times on iron pipes and things like that that are buried into the ground. You might see other metals kind of in contact with that as well. So I hope you enjoyed this video. If you enjoyed this video, if you liked this video, if this was fascinating and you learned something from it, then please, by all means, share this video, like this video, hit that like button right there. And also make sure you subscribe to my channel, hit that notification bell. When you hit the notification bell, make sure you click all so that way you can be notified by any and all videos that I post. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I'd love to hear from you. Thanks for joining me and have a great day.